Hello learners, I'm Subhalakshmi Lamba and I'm in the Faculty of Physics at the Indira Gandhi National Open University. The topic of today's lecture is kinematics of angular motion. This is the third part of this lecture and you have already gone through lectures 1 and 2, I hope. Let me just recap for you what we did in the previous two lectures. We studied in lecture 1 what is angular motion. That is, angular motion is the motion about a fixed point or about a fixed axis. In lecture 1, we also covered a definition of angular position, which is one of the important kinematic variables for angular motion. In lecture 2, we talked about angular displacement, angular velocity, angular acceleration, and we also introduced the kinematic equations for angular motion. So what is angular displacement? If you move from a position of theta 1, angular position of theta 1 to an angular position of theta 2 in a time t1 to t2, then the angular displacement is given by theta 2 minus theta 1. As always, this is measured in radians. We talked about the average angular velocity, which is nothing but theta 2 minus theta 1 by t2 minus t1. We described the instantaneous angular velocity, which is also called the angular velocity, which is nothing but the rate of change of angular position. Omega is equal to d theta by dt. We talked about the average angular acceleration, which is given by omega 2 minus omega 1 by t2 minus t1. We can also write that as delta omega by delta t. We talked about angular acceleration, which is nothing but the rate of change of the angular velocity. Finally, we introduced the equations of kinematics. There are 3 of them and they are analogous to what you have studied for translational motion, except that here we talk about angular speed, angular acceleration and angular displacement. In this lecture, we will first work out one example of the application of the equations of kinematics to angular motion. Then we try to understand why we use angular variables to describe angular motion. Finally, we try to relate the variables for translational and angular motion. We also describe the tangential speed. This is the translational speed for circular motion. As I said, we will start this lecture with an example of the application of the equations of kinematics for angular motion with constant angular acceleration. You can look up these equations. They are equations 11.8 A, B and C in your unit. So, let us first understand the question. A wheel starting from rest has a constant angular acceleration of 4 radians per second squared. And it turns through an angle of 18 radians. Calculate the final angular speed and the time taken. So what are the things that you know? You know that the wheel is starting from rest. So the initial angular speed, which is omega 0, is 0. You know that it has turned through an angle of 18 radians. So basically, if you take theta 0 is 0, that is the initial angular position. The final angular position minus the initial angular position is 18 radians. That is, theta minus theta 0 is 18 radians. Finally, you know that the constant angular acceleration of the wheel is 4 radians per second squared. What do you have to calculate? You have to calculate the angular speed at the time in which it has moved through an angle of 18 radians. So basically, you have to calculate the angular speed after the wheel has turned through 18 radians, and you also have to find the time it takes to turn through 18 radians. How do you do that? On the left, you find that I have written down the 3 equations of motion, the 3 kinematic equations that are available to you. And you have to pick one of these to calculate the first thing, and suppose that we want to calculate the time. Let us start with the first equation. Omega is equal to omega 0 plus alpha t. What do you know in this equation? You know alpha, you know omega 0, but you do not know t. So basically, you cannot use this equation because you have 2 unknowns. T and omega are both unknown. Look at the second equation. You know theta minus theta 0. You know omega 0 and you know alpha. It has therefore just one unknown, which is t. So you can use this equation to calculate t. The third equation is omega squared is equal to omega naught squared plus 2 alpha theta minus theta 0. You know theta minus theta 0, you know alpha, you know omega 0. You can use this equation to calculate omega. So depending on whether you want to calculate t first or omega first, you can use either of the two equations, the second or the third. Now I choose to calculate t first. So to do that, I use the second equation, and in that, what do I substitute? I substitute omega 0 is equal to 0. I substitute theta minus theta 0 is equal to 18 radians, and I substitute alpha, which is the acceleration, is equal to 4 radians per second squared. I want you to work this out for yourself, and you will find that t is equal to 3 seconds. So now what do you know? You know the time it has taken for the wheel to turn through 18 radians. What do you not still know? You still do not know what is its angular speed after 3 seconds. So now we calculate the angular speed after 3 seconds. Once again, let us decide which of the three equations we can use. You can understand for yourself that you can use either the first equation or the third equation, because these are the equations in which you have just one unknown. So I use the first equation to calculate omega because it looks to me to be simpler. So in this equation, I substitute omega 0 is equal to 0, alpha is equal to 4 radians per second squared, and I use the result which I have calculated in the previous slide, that is t is equal to 3 seconds. This gives me the answer for omega at the end of 3 seconds, which is 12 radians per second. Please remember, whenever you work out a numerical in physics, you must use the correct units. Now, let us come to the discussion on why we use angular variables for angular motion. We come back to our favorite example, which is that of a wheel which is rotating in a plane, and once again we assume it is rotating counterclockwise, and the axis of rotation, which is fixed, passes through the center of the wheel. We know that if we pick out any point on this wheel, say I have picked out 2 points, P1 and P2, each of these points will undergo circular motion about the center of the wheel. And because the wheel is rotating counterclockwise, this motion is also counterclockwise. Now suppose both the points start from the x-axis, that is the reference axis, and the zero angular position for P1 is at A1, for P2 it is at A2. Starting from A1 and A2, let us assume that both of them complete one complete revolution and come back to the same points, that is their starting points. So basically P1 comes back to A1, P2 comes back to A2. Suppose the time taken for this single revolution is t, and you know that since both of them come back to their starting points at the same instant, this time is the same for both these points P1 and P2. So basically you have that P1 returns to A1 in time t and P2 returns to A2 in time t. So what is the angular speed for both these points P1 and P2? That will be the angle covered divided by the time taken. Now, since both of these points have undergone one complete circle, so they have covered 2 pi radians of displacement. So the angular displacement delta theta for both these points, because it is an angular displacement, it is the same for both these points, and that angular displacement is 2 pi. Both of these points come back in the same time, and so the time taken is also t for both of them. So basically what you can understand is that the angular speed for both these points on the rotating wheel is 2 pi by t. So what have you understood from this? You have understood that the angular speed is the same for all the particles situated on a rotating object. Obviously, it is not so for all those particles which are located on the axis of rotation. Other than that, the angular speed is the same for all particles situated on a rotating object. This should explain to you why we choose to use angular variables for angular motion. You have studied in translational motion that in translational motion, the velocity and acceleration are the same for all points on a translating body. However, in case of angular motion, we use angular variables because the angular speed is the same for all particles which are located on a rotating object. Now, let us try to relate the variables for angular and translational motion. Is it possible to say anything about the translational speed of objects on a rotating body? So, let us once again consider a rotating wheel and 2 points on this rotating wheel, P1 and P2. One of them is closer to the center of the wheel, one of them is closer to the rim of the wheel. So, can you say anything about the translational speed of these 2 points on the wheel which is rotating? Do you think one of them will move faster than the other, or do you think that both of them will have the same translational speed? Remember, this time we are talking about translational speed and not the angular speed, by which I mean that I am trying to calculate the distance covered by each of these points in unit time and not the angular displacement per unit time. So, we know that the angular speed is the same for both P1 and P2. We don't have to think about that. Now let us just calculate what is the time taken for each revolution. We have already discussed this earlier, and this time is nothing but 2 pi by omega, where omega is the angular speed of for each of these points. So what is the distance covered by P1? P1 is on the rotating wheel. It covers a circle, and the radius of this circle, if we consider that to be R1, then we can see that in one revolution, the point P will cover a distance of 2 pi R1. So the speed of P1, and this I'm talking about the distance covered per unit time, is nothing but 2 pi R1 by T. 2 pi R1 is the circumference of the circle in which P has moved in one complete revolution. Similarly, we can write the speed of P2 as 2 pi R2 upon T. 2 pi R2 is the circumference of the circle in which P2 is moving. That has a radius R2, and so the distance covered by P2 in one revolution is 2 pi R2. The time taken once again is just T, so the velocity, the translational velocity, is nothing but 2 pi R2 by T. So, as I said, V1 is 2 pi R1 by T and V2 is 2 pi R2 by T. But we know that R2 is greater than R1. P2 is moving in a larger circle than P1. So, what can we say? That because P2 covers a larger distance in the same time as P1, therefore, V2 must be greater than V1. So, what do you understand? That further an object or a point is from the center or from the axis of rotation, the greater is its speed. This is not what we said about the angular speed. We know that P1 and P2 have the same angular speed, but you can see that because P2 covers a different distance from P1 in the same time, they have different translational speeds. So can we relate this angular speed and the linear speed V? Yes, we can. And how do we do that? We know how to relate theta to a distance. We say that theta is measured as S by R. Remember, theta is in radians. Both S and R have units of length. So theta is equal to S by R. So we can write S is equal to R theta. What then is the linear speed? The linear speed is ds by dt, which is nothing but the derivative of r into theta. Theta continues to be measured in radians, but r has a unit of length. So the linear speed is nothing but r d theta by dt. We've already studied what is d theta by dt. It is nothing but omega. So basically the linear speed is equal to r times the angular speed. Angular speed is in radians per second. R and s have units of length. So you can write the SI unit of V as meters per second. So basically, we have that the linear speed is related to the angular speed by V is equal to R omega. And here I have shown it in this diagram. You also see that I have indicated that the velocities V that we have measured is actually at right angles to the radial vector. We will prove this shortly as an application. So how do you know that the speed is directed at right angles to the radial vector. Now, for this, we use some concepts which are related to block 1 of your course, in which you have studied the basics of vector algebra, the basics of differentiating vector functions, the basics of dot and cross products. So, we know that for circular motion, the particle is always at a constant distance from the center of the circle. So, suppose this distance is r, which is the magnitude of the position vector of the moving particle at any point of time. So, we can write that r is constant, obviously, because it is circular motion, and r squared is equal to r dot r. You know this from your understanding of dot products or scalar products. So, r dot r is a scalar product which is equal to the square of the magnitude of r. Let us recollect what is the derivative of a scalar product. If you have two vectors a and b, their scalar product is a dot b. We write the derivative as the scalar product of the derivative of a with b and plus the scalar product of a with the derivative of b. So basically there are two terms in this derivative. You take the derivative of each term separately and then add it. So differentiating this scalar product r dot r with time, you know that r dot r is constant, so ddt of r dot r is 0. So, because the derivative of a constant is 0, so ddt of r dot r is 0, and from that we get that r dot dr by dt is equal to 0. Now, dr by dt is nothing but the speed or the velocity of the particle in the moving on the circular path. So, basically what you can write is that r dot b is equal to 0. From your understanding of scalar products, you also know that if the scalar product of two vectors is 0, then either the vectors themselves are null vectors or they are at right angles to each other. Now, since we can see for ourselves that neither of these vectors is a null vector, we have to believe that v is always perpendicular to r. So, this helps us to understand why we have the linear speed always along the tangent to the circle. So basically, if your particle is moving in a circular path, the angular velocity is directed along the axis of rotation, but your linear speed is always tangential to the radial vector or the position vector. So the velocity is always perpendicular to the radial vector. So what do we know about the time period of revolution and this tangential speed? We have already said that the time period is nothing but 2 pi by omega seconds. Since you know that v is equal to r omega, we can relate t to this, the time period to the linear speed as well by using the radius. So t is nothing but 2 pi by omega, which is 2 pi by v by r. So it is 2 pi r by v seconds. So basically you can write the time period of revolution either in units of the angular speed or the linear speed. Now we talk about the acceleration for circular motion. We know that circular motion may be uniform or non-uniform. What do you understand by uniform circular motion? Uniform circular motion is motion in which the angular speed is a constant. So basically the angular acceleration alpha is 0. So let us now discuss the acceleration first for uniform circular motion. We know that for circular motion, r is a constant. Because it is uniform circular motion, omega is also a constant, and we know that because once again omega is constant and r is a constant, v must be a constant because v is equal to r omega. Similarly, you know that the direction of the angular velocity is also fixed along the axis of rotation. It can be either along the positive z-axis or the negative z-axis, depending on whether you have counterclockwise or clockwise motion in the xy plane. So we know that the vector omega is also a constant. So then what does change? What changes is that the direction of the linear speed, which is tangential to the radial vector at each point of motion, is what is changing. So you can see in this figure that depending on the position of the particle, the velocity vector, which is at right angles to the radial vector, has a different orientation at every instant of time. So basically, although the magnitude of V is constant, the direction of V is not constant, and therefore we know that we have a varying velocity. If you remember, whenever there is a change in the velocity, there is an acceleration. So this tells us that even to keep a particle moving with a constant angular speed and a constant linear speed in a circular path, you must have a finite acceleration. This is called the centripetal acceleration for uniform circular motion. So, what do you know about the centripetal acceleration? You know that V is perpendicular to R, and the magnitude of the centripetal acceleration is V squared by R. And because you know that V is equal to R omega, you can write that the centripetal acceleration is equal to omega squared R. So, you have a finite acceleration for uniform circular motion, and this is the centripetal acceleration. So the magnitude of the centripetal acceleration can be written in terms of either the linear speed or the angular speed, and A is equal to V squared by R, and it is also equal to omega squared R. So far we have talked about the magnitude of the centripetal acceleration. We also need to know the direction of centripetal acceleration. To determine the direction of the centripetal acceleration, we use the same technique that we use to calculate the direction of the tangential speed. So we know that for uniform circular motion, the tangential speed has a constant magnitude. So basically V is constant, which also means that the scalar product of the vector V with itself is a constant. We take the derivative of V dot V with respect to time. And what do we get? d dt of V dot V is nothing but V dot dV by dt, and that is equal to 0 because the derivative of a constant is 0. So once again, we use the same logic to say that V and dV by dt, because the scalar product is 0 and neither of these is a null vector, they must be perpendicular to each other. So basically what you get from this derivation is that V dot dV by dt, which is also the acceleration, is equal to 0, means that the acceleration vector A is perpendicular to the velocity vector V. So that tells us that A is directed either along the radial vector or opposite to the radial vector, because in both those cases you would get V dot A is equal to 0. You know that the radial vector or the radial direction is at right angles to V, and V dot A being 0 means that A has to be either along R or opposite to the direction of R. So basically what you have proved is that velocity is always perpendicular to the acceleration vector, but we have yet to determine whether the acceleration vector is along R or opposite to R. That means, is it directed towards the center of the circle or outwards from the center of the circle? So let us now try to find the derivative of R dot V. You know that R is perpendicular to V. So the derivative of R dot V has to be 0. Now, if you do the calculation in the same way as you did the calculation for taking the derivative of V dot V or R dot R, you will come to the conclusion that R dot A plus V dot V is 0. Here we have made the replacement that dV by dt is nothing but the acceleration vector. So basically what you get is that R dot A plus V dot V is equal to 0, or in other words, R dot A has to be equal to minus V squared. Minus V dot V is nothing but minus the square of the magnitude of the velocity vector. So we can say that because R and A are in the same, along the same line, therefore the very fact that R dot A is negative, the square of V is always positive, so R dot A has to be opposite, they have to be directed opposite to each other. So basically R and A lie along opposite directions. So basically A will be directed towards the center of the circle. So acceleration is radial and it is always directed towards the center of the circle. Now, using the relationship r dot a is equal to minus v squared, you can also write down that a is equal to v squared by r, using the condition that r and a are at 180 degrees to each other. So basically, r dot a is minus ar and minus ar is equal to minus v squared, which tells us that a is equal to v squared by r. In lectures 1 and 2, we defined the angular kinematic variables, which are basically angular position, angular displacement, angular velocity, and angular acceleration. We also introduced the equations of kinematics for angular motion with a constant angular acceleration alpha. There are 3 of these equations, and you know that these are omega is equal to omega 0 plus alpha t, theta is equal to theta 0 plus omega 0 t plus half alpha t squared, and omega squared is equal to omega 0 squared plus 2 alpha theta minus theta 0. So using these 3 equations of kinematics for angular motion, you can determine the angular speed, the angular displacement, and the time taken for any particular angular displacement in different ways depending on what is available to you as an input. Now in this lecture we discussed why we use angular variables for angular motion. We know that we use a set of variables for translational motion, and we keep in mind that the velocity of an object or a particle which is undergoing translational motion is the same for all points of the object. So in the same way, we use angular variables for angular motion, because if you have a rotating object, you will find that the angular speed is the same at each point of the rotating object. So basically, we use angular variables for convenience when it comes to describing the motion of a rotating object. Now, we also want to know whether there is any relation between the angular variables we described and the translational variables which you use for translational motion. You find that you can relate the angular variables and the translational variables. In fact, you can define a linear speed for each point of a rotating object. And you also find that this linear speed is equal to r times the angular speed. What is r? It is the radius of the circle in which the particle is moving. Omega is the angular speed, and v is equal to r omega, defines the relation between the linear speed v and the angular speed omega. You have also seen in this lecture that the further a point is from the axis of rotation, when it comes to a rotating body, the greater is its speed. So if you have a rotating wheel and you have a point near the rim of the wheel, then it is going to be moving faster than a point towards the center of the wheel. Also, you saw that the linear speed is always at right angles to the radial vector. So at each point of circular motion, the speed is at right angles to the position vector at that point. So the direction of the speed is tangential to the circle at all points. Now, we said that we basically study 2 types of circular motion. One is uniform circular motion, in which the angular acceleration is 0. So basically, the angular speed is a constant for uniform circular motion. And because the angular speed is a constant and it is moving in a circle, so v, which is equal to r omega, is also a constant. So although you have a constant magnitude for r, omega and v, the direction of v changes at each point of its motion, because we know that the linear speed is at right angles to the radial vector at each point. So v does not have a constant direction, and since the velocity is changing, there has to be a finite acceleration. This finite acceleration is called the centripetal acceleration, and it has a magnitude which you can define either in terms of the linear velocity v or in terms of the angular velocity omega. So a is equal to v squared by r, and A is also equal to omega squared by r. We also discussed and determined the direction of the centripetal acceleration. We derived that the centripetal acceleration is always at right angles to the velocity, and it is directed towards the center of the circle in which the particle is moving. So basically the centripetal acceleration is directed towards the center of the circle in which uniform circular motion is taking place. In the next lecture, we will talk about non-uniform circular motions. In non-uniform circular motion, you have a finite angular acceleration. So, although the particle is moving in a circle, its angular speed is changing, and because of that, you have another acceleration. Now, and you will also learn to calculate the effective acceleration, which is a combination of the radial acceleration and the acceleration which arises from the change in the magnitude of the angular velocity. So you will define the total or the resultant angular acceleration vector for non-uniform circular motion. Thank you for watching this video. I hope to see you soon in the next lecture.